Okay, so picking up where we left off in the last video, we were working over S1, which is the right half of the sphere, and all I did is I have the integral written down here. I just moved it up here, and then originally I had a sine squared phi here. I said I was going to replace that with a 1 minus cosine squared phi. That's because now I'm going to do two substitutions. Here I'm going to let u equal cosine of phi, so that du is negative sine phi d phi. Over here, I'm going to let w equal sine of phi, so that dw is cosine of phi d phi. Now, that means here, I've got the sine phi that I need for my u sub. We need a negative sign, so I'm going to introduce a negative and counterbalance with a negative on the outside. So this will become, this first integral becomes negative, the integral from 0 to pi, the integral from cosine of 0, which is 1, to cosine of pi, which is negative 1. That negative and that sine of phi get absorbed into the dw, so this is just going to become 1 minus w squared. That's still multiplied by this whole thing, a cubed sine theta cosine theta plus a cubed sine squared theta. But now it's dw, that absorbs the sine phi and the negative sign, d theta. Plus, this one becomes the integral from 0 to pi. And then we get w is going to be sine of 0 to sine of pi. Oh, I like that. Okay, now this entire integral is gone. Okay, because I'm going to be integrating a cubed w squared sine theta dw d theta, but because I'm integrating from 0 to 0, this entire integral is just 0. So we only need to worry about this one. Okay, so that's going to be negative. Integral from 0 to pi. I'm going to get here w minus w cubed over 3. That's evaluated between negative 1 and 1. And then times a cubed sine theta cosine theta plus a cubed sine squared theta. And we'll have to integrate that d theta. Okay, so let's see. If I plug in negative 1 here, I'm just going to evaluate this part. When I plug in negative 1, I'm going to get negative 1, minus negative a third, so plus a third, minus, when I plug in 1, 1 minus a third. So that's negative 2/3 minus 2/3. This is negative 4/3. That's a constant, so I'm going to factor it out. Combined with that negative sign on the outside, I'm going to get 4/3 integral from 0 to pi of a cubed sine theta cosine theta plus a cubed sine squared theta d theta. All right, let's break that up into two integrals. Okay, so we've got 4/3 of the integral from 0 to pi, a cubed, I'm actually going to just factor that out, so that's going to be 4a cubed over 3, sine theta, cosine theta, d theta, plus, I'll still have the 4/3, and I can factor out this a cubed again, so 4a cubed over 3. But do be careful, that 4/3 applies to both of them, so make sure you distribute it when you break it up. And then it's the integral of sine squared theta d theta. I'm liking this because I'm going to do my same w substitution. If I let w equal sine theta, dw is cosine of theta d theta, but then this becomes 4a cubed over 3 integral from 0 to 0 of w dw, and that's just 0. So the only thing that's going to contribute something other than 0 is this piece right here. So I want to remember, whoops, this is still from 0 to pi too, isn't it? I want to remember that if I'm integrating an even power of either sine or cosine, I'm using the double angle formula for cosine. So we've got 4a cubed over 3, integral from 0 to pi. Sine squared is the same as 1 minus cosine 2 theta all over 2 d theta. In the interest of time, I'm not going to rederive that here because we've derived it several times in the past. But if you don't remember how we got that, you want to look back, make sure you know how to derive that, because these even powers of sine and cosine do show up an awful lot. Okay, I'm going to cancel that 2 with the 4, so that becomes a 2/3 on the outside. And then I'm going to do a quick, I'm just going to recycle u and do a u sub. So u is no longer cosine of phi. We're done with that u. All right, so u is 2 theta, so du is 2 d theta. Now, that means I need a 2 on the inside, which I can counterbalance with a 1/2 on the outside, and that's going to cancel with that 2 that was still there. So we'll end up with just a cubed over 3. The integral from 0 to 2 pi, make sure you remember to change to your w values, your u values, 1 minus cosine of u du. All right, we are almost there with the first of 2 surface integrals. Okay, so a cubed over 3. We're going to have u minus sine u, and that's evaluated between 2 pi and 0. So that's going to be a cubed over 3 times at 2 pi, I get 2 pi minus 0. Minus at 0, I just get 0 minus 0. So that's going to be 2 pi a cubed all over 3. Now, that's just this piece. 2 pi a cubed all over 3. Okay. I need to add this piece to it. But I'm supposed to get 2 pi a cubed all over 3 as my answer. I'm really hoping at this point that this surface integral is 0. If it's not, something's gone wrong, and we're going to have to figure out what. Okay. But I pretty much know that my surface integral had to be over both pieces, because this by itself is not the boundary of E. So if you just evaluated that, you might say, oh, yay, I got the same thing, but you got to add that in. Okay. So for S2, we're evaluating now the double integral over S2 of f dotted with n ds. I'm going to need to parameterize that surface. But notice that surface is in the xz plane. So it's y equals 0. Okay. So I can actually parameterize this as r of, I'm just going to use x and z as my parameters, because y is a function of x and z. It just happens to be a constant function. So r of xz would be x0 z. Okay. All right, now you might have noticed how we're going to know that this integral is 0 at this point. I'm going to keep working just because I want to actually set up this parameterization, again, just for some extra practice. Okay, so that would mean that then if I go to write this out, it would become the double integral over d. Now d would be the projection of this onto the xz plane, because I'm viewing y as a function of x and z. So that would be this disk of radius a in the xz plane. I would write my vector field f in terms of my parameterization. Now here's how we're going to see that we're going to get 0. Because my parameterization has y being 0, but my vector field was y, y, y. So I'm going to get 0, 0, 0 dotted with, and I am going to just take the time to write out what we're getting, okay, this I would want to be parameter oriented so that we're pointing leftward. So I would want the y component here to be -1. If I have a -1 here, then what goes here is the partial of y with respect to x, and what goes here is the partial of y with respect to z. Again, I'm viewing this as y as a function of x and z, but both of these are just 0. Okay. So just wanted to remind you how we can get that normal vector pretty much by inspection. This is, remember, happens to be a unit vector in this case, but in general, if these guys weren't 0, this would be the non-normalized normal vector that I'd be dotting with. Of course, we're just integrating now 0 dA, so we're going to get 0. So the integral over S, the two-part boundary, is 2 pi a cubed over 3 plus 0, which is 2 pi a cubed over 3, which is in fact what we got when we used the divergence theorem. Again, this is a problem that the only reason I would actually do this as a surface integral is because it's fun to get extra practice, or because your teacher told you to, said do this problem both ways. Okay, definitely easier to use the divergence theorem in a problem like this.